Hey folks, welcome to another week of machine learning and data mining, advanced data mining, machine learning. What a complex title, you know. This week's podcast will be starting with the chapter on high-dimensional data. As promised, we'll talk about high-dimensional data, and also as promised last week, this will be a very, very huge, a very, very large chapter. At least in the context of, or in terms of content. So if we have a look at the outline of this chapter, you see we will have a lot in front of us. So probably it takes us 3 to 4 or even 5 weeks to go through all of that stuff. So we'll have an introduction to feature spaces again today or this week, and also a couple of challenges for high-dimensional data. And we will also talk a little bit about the first kind of solutions for these challenges, which will be supervised feature selection, part of that at least today, I think, or this week. And then we will talk about feature reduction metric learning. So all that stuff is typically in the pre-processing steps of our machine learning data science process. And then afterwards, or at the end, we'll talk a lot about clustering high-dimensional data, because most of that stuff here, well, not all of that stuff, of course, but most of that stuff here is supervised. And of course, we can do principal component analysis and these things here, which are unsupervised. But especially in the unsupervised setting, we will have a lot of challenges for high-dimensional data, and there are dedicated approaches or dedicated things to do when in the context of clustering when it comes down to high-dimensional data, and we'll talk about that also a lot. But we'll start with an introduction to feature spaces. So that will be our first part here, and feature space is somehow revisited. Let's have a look what is actually a feature space. And remember from last week, there are different ways to get feature representations, these kind of canonical representations, but we'll focus on these kind of manual feature transformations or feature extractions. So we are not talking about representation learning and stuff like that. So we are talking basically about feature transformations. So what is a feature transformation again? So typically we consider the following spaces. U is the universe of the raw data, so to say. So our data that we get from somewhere is the raw data, has some specific representation, and the representation is denoted by U. That is the space of our raw data, and we want to transfer this into a canonical space, which is this F here, which is typically part of R to the power of n. So we will have an n-dimensional feature space, and the features, all of these n features will be real valued. So that is the basic idea of the feature transformation, which is denoted here. It's just a mapping, which is denoted here as F, from this universe of the raw data into this canonical form of an n-dimensional feature space. And once again, the n features here are real valued. So that is the set of real numbers, of course. So we want to transform each object, each raw object, into this canonical representation, which is a kind of table of n numerical features, so to say. And the feature transformation, together with a kind of similarity notion, gives us a so-called similarity model. So a similarity model is defined actually by a kind of similarity function. So the similarity model for the raw data, you can take two objects from the raw data, so to say, and you will get a quantification how similar these two objects are, actually these two raw objects are. And we take somehow the not the bypass, or in that case the extra round through this feature transformation. So we take for each of the two raw objects, we take the feature representation of these two raw objects, which is f of p. Of course, p is the original one in U, and f of p is of course then in R to the power of n. The same holds true for f of q, and we apply some kind of similarity measure or distance measure, which is then a dissimilarity measure, which is computed on the feature representation, on the canonical representation. Yeah? So a little bit complicated, don't get confused about it. Actually, a similarity model consists of a feature mapping, a feature transformation, and a similarity measure on these in these canonical feature representations. Yeah? So that is the basic idea, actually. Yeah? That's what we typically need in order to do similarity search, of course, so querying some databases, but also, of course, to do data mining and machine learning, because very often you just search for something which is similar. Yeah, so the patterns that we already discussed last week, clustering, classification, and stuff like that, that's mostly about similarity. So finding similar objects, finding groups of similar objects, finding the characteristics of similar objects from one class or whatever. Yeah, so that is actually what you need to do data mining and machine learning, old school, so to say. Yeah, not with deep learning methods in that case. Yeah, some comments: similarity or dissimilarity. This is stated here. It could be this sim here, this function here, or this measure. It's a function, can be a similarity measure or a dissimilarity measure. In that case, it's a distance measure. What does that mean? Well, dissimilarity is measured very often instead of similarity. Yeah, so we look for groups of similar objects or some patterns about similarity, but instead of similarity, typically or very often we measure distances, dissimilarity. This is a small but very, very important difference, because a similarity measure, of course, assigns high values to similar objects, and a dissimilarity measure or a distance measure is the other way around. It assigns low values to similar objects. Yeah, so we have to be very clear what actually our measure is. Is it a dissimilarity measure, distance measure, or a similarity measure? Because, as you probably know from k-means, for example, if you look at the sum of the squared errors, then you assume that's a distance measure, a dissimilarity measure. Yeah? So if you have a similarity measure between the points and the cluster representatives, then you want to minimize that and not maximize that. Yeah? The other way around, sorry. Then you want to maximize it, not minimize it. Yeah? So anyway, so keep that in mind. Of course, it's a big difference, even though it's just very, very intuitive. Yeah. Yeah, the design of this feature transformation, F is the feature transformation, the mapping here, yeah, and the similarity or the distance measure are already important assumptions about the patterns we want to find later in the data. Yeah, because of course our feature mapping should somehow take into account the most important features for a given application, and the similarity measure, of course, should then give well, it's a similarity measure. If it's a similarity measure, it should give high values, meaning they are more similar to most similar objects from the raw representation, and the other way around, of course. Yeah, so and since we are doing that typically manually, there are already first assumptions about what kind of patterns we want to find, what kind of semantic semantic things we want to grab out of the data. Yeah? And we talked about that. The mapping and also the similarity measure or distance measure can be derived manually, explicitly by the transformation, maybe implicit by some kernel, but still we have to somehow manually do that. And of course we could also do that automatically, not in all cases, but sometimes we can do that using representation learning approaches like deep neural networks and stuff like that. You know? But once again, we are talking about the first part here. We're talking about explicit or implicit feature transformations, basically about explicit feature transformations. Yeah, we'll talk a little bit about kernels also, but not too much here.